establish and perish all the same.
I'm Nicolas Bellouin. I work at the University of Reading in the UK, but I used to be at the Met Office Hadley Centre. I was in charge of aerosol modeling in the unified model. And I will talk to you today about aerosol modeling. So it's going to be very much an introduction course, so we will not be going very deep into the subject. But the aim is basically to detail what are the important processes that we need to represent in global models, and how we validate the models, how do we know whether they're good or not. So let's start, of course, by reminding everyone of what is an aerosol. So the definition of aerosols is that there are all the particles, solid or liquid, that are in suspension in the atmosphere. So that's a pretty wide definition, but we exclude from that the cloud droplets and cloud ice crystals, because the main reason is because they obey rather different physics. A few pictures of aerosols for you to give you an idea. So those are electron microscope pictures. Here on the left, you've got mineral dust aerosols. So that's basically grains of sands. On the middle panel, you've got more industrial, let's say, man-made aerosols. So that's sulfate or soot. And on the right, sea salt aerosols generated over the ocean. So aerosols are emitted into the atmosphere both by natural processes and by our activities, as we'll see. So why are we interested in modeling aerosols? Well, there are quite a few applications for them. The first one, historically, was for visibility. Aerosols affect visibility, and that was one of the main reasons why we studied them in the first place. Then they affect air quality and human health, which are obviously an important motivation for the study. They affect the relative budget of the Earth, so the energy budget. So they have application in both weather forecasts and climate modeling. They affect the relative budget by interacting directly with radiation or by modifying the properties of clouds. Typically in the atmosphere, most liquid clouds form onto aerosol particles. They affect, well, they're actually part of the great biogeochemical cycle of the Earth. So the sulfur cycle is the most obvious one, but they also affect the carbon cycle via changes in the growth of vegetation. And they affect other ecosystems, like life in the ocean by bringing nutrients, and also vegetation growth, again, by bringing nutrients into some regions. And perhaps more recently, we are also interested in aerosols from volcanic eruptions because volcanic ash plumes can affect air traffic. So during this presentation, feel free to ask me any question you want as we go. The bad news is that I will also have some questions for you, and your participation will be much appreciated. And the first question is, okay, so we've got all those applications for, and those motivation to study and model aerosols. So what are the properties of aerosols that we should be able to model in order to answer all those questions? If anyone has an idea. The size, yes, yeah. Say again, sorry? Concentration, of course. How many aerosols there are, yeah. Yep. composition, yeah. Yeah, excellent, yes, the origins of the particles. So, excellence, you've got most of, well done, yes. You've got most of the properties on the list. So, indeed, we need to know the mass concentration, so how many aerosols there are. We need to know their size and number. We need to know their chemical composition, what they are made of, their mode of production, so how they got emitted into the atmosphere in the first place. Some other things we need to know is the mixing state. We'll see what that is in a few moments. Whether they are soluble or not, and whether they can uptake water as they reside in the atmosphere. And finally, it could be interesting also to know their shape, because it does impact on some of the properties, for example, their ability to interact with radiation. So let's start with aerosol mass. That's obviously one of the main outcome of an aerosol model. And here I show, for example, the MAC forecast of PM10 aerosol. So PM stands for particulate matter. This is the metric that is commonly used by air quality people. So PM10 is basically the mass concentrations, typically in micrograms per cubic meters, of aerosols smaller than 10 microns in diameter. So here is a forecast for October last year, and you see that's so relatively high concentrations of aerosols over northern Europe, the Benelux, north of France, and the south of the UK, extending all the way to Germany and Central Europe. Also high concentrations, typically in the Po Valley in Italy. So all of these are linked to industrial and agricultural activity in our continent. Typically in aerosol models, we don't use the concentration as a variable of the model. The main reason why we don't do that is because the density of air varies. So it makes it a little bit awkward to use that as a variable of the model. So in general, most models use the aerosol mass mixing ratio, which is the mass of aerosols per kilogram of dry air. Okay, so one of the other important properties we need to know and model is the size of the aerosols, and more specifically the size distribution. So the size distribution, here I show an example taken from aircraft measurements, so that's an average over many campaigns by the UK Met Office aircraft. So the size distributions simply gives the number of particles as a function of their radius. So first, you see that we work on logarithmic scale, both in terms of number and in terms of radius, and that's because there is a wide and very large variation in the number of particles in the atmosphere, both spatial variation and temporal variation. And there is also quite a wide range of possible particle sizes. The other thing you see is that the size distribution is not smooth, so you don't have the same number of particles for every possible radius. What we see instead is that the size distribution has maxima at different values. They tend to vary locally, and those maxima are called modes. So they are the aerosol modes, and I will mention that name quite a bit in this course. So the question here is, why do you think there are those maxima and minima in the size distribution? Why isn't the size distribution smooth? That's a more difficult question, yeah. Maybe at the back, yeah, here. Yeah, there are some processes that indeed transfer mass from the smaller mass or number from the smaller particles to the larger ones, yeah, that's one reason. Yes, exactly. So the way they are also emitted, emissions are preferentially depending on the process of the emission at some sizes. And indeed, the way the aerosols are removed from the atmosphere also depends very much on the size, and the sum of all those processes tend to, how can I say that, favor some particle sizes. So here is a table that shows the conventional way we group aerosols together into modes. So there are in general three types of modes that we tend to distinguish. Of course, an actual size distribution could have more modes of different types. First, starting with the smaller particles. So by convention, we tend to put the limit at 0.05 microns, so that's 50 nanometers. And so this mode is named the nucleation or icon or fine mode, depending on the paper and the scientist you talk to. Typically, those particles originate from conversion from the gas phase to the aerosol phase. Then you've got the accumulation mode, which is also sometimes called fine mode, for particles of intermediate size, so between 50 nanometers and 0.5 microns. So this mode, as a name accumulation may indicate, typically originates from the coagulation of nucleation or icon mode particles into larger particles. Could originate as well from the condensation of gases onto existing aerosols. And then combustion processes tend to be relatively efficient at emitting aerosols directly into the accumulation mode. And finally, we've got the coarse mode for larger particles. And here, the production process is mainly through friction. So typically wind speed acting on bare soils or deserts area, for example, or acting over the ocean. And we'll see a little bit more on those processes later. So the aerosol distribution, it's useful to be able to describe it mathematically as a mathematical function. So to do that, we need a function that is able to cover a wide range of particle sizes and cover large variations in number. So there are several choices. You may hear when you read about aerosols about the modified gamma distribution or the Young distribution. The most used in aerosol models currently is the log normal distribution, because it's been shown that it describes relatively well the typical distributions that we can observe in the atmosphere. So mathematically, this is what it looks like. What matters here is that it takes three parameters. The first one is the total number, so that's the total number of particles that you want to distribute across a range of sizes. The second parameter is the mean radius. It happens mathematically that in the log normal distribution, the mean and the median are equal. So it gives you where the distribution is centered in the range of size. And then the final parameter is the standard deviation of the distribution, so how wide it is, and its ability to cover smaller and larger sizes than the mean radius. So looking at how this log normal distribution looks like, here I show total aerosol size distribution as a superposition of 3 log normals. So the log normal here, so we are in log-log space. So the log normal looks like a normal distribution, so very much like a bell curve. The size distribution of the number here is shown on the left, but you can do the same for the size distribution of the surface and the size distribution of the volume of the particles. And you see on those plots that the 3 different types are dominated by different kinds of particles. So the size distribution of the number is very much dominated by the smaller particles, which sounds logical. So the smaller particles are more numerous in the atmosphere in most conditions. The surface of the aerosol, though, is not contributed by the smaller particles, but mainly by the particles of the accumulation mode, which is for intermediate sizes. The surface will typically control the interaction of aerosols with radiation, especially at short wave or visible wavelength. So this is a class of particles that is of most interest for studying aerosol interactions with radiation. Then finally, the distribution of the volume is dominated by the larger particles, as you would expect. And of course, the volume is directly related to the mass. So it means that the larger particles will provide most of the aerosol mass that you have in the atmosphere. Okay, so moving on to chemical composition. So the chemical composition of the aerosol varies very much spatially and temporally. And here is a nice diagram taken by, from a paper by Jimenez that summarizes, I think that's aerosol mass spectrometer measurements at different places, mostly in urban and in the countryside outside large cities of the North Hemisphere. And what you can show is that for each measurement, they summarize the aerosol composition. So in red, you've got sulfate aerosols, in blue, nitrate, and then moving on to organics in the different shades of green. And you see that depending on the location, one chemical composition will dominate typically over the others, but in most locations, it's very much a complex mixture of different aerosol species. So there is a wide variation spatially, but also temporally. So if we look, for example, at Manchester in the UK, in winter, the aerosol is dominated by organics in terms of composition, whereas in summer, you see that nitrate and sulfate make about half of the aerosol mass. So the ability of a model to be able to represent those changes in the aerosol composition is quite important in determining the skill of the model. Okay, so I just mentioned some of the main aerosol species that we are interested in. Here is a more complete list. First, and certainly historically, the first one that has been included in most global models, at least for climate applications, is sulfate. So that's the SO4 ion. Typically in the atmosphere, it is found as sulfuric acid or ammonium sulfate, depending on its state of oxidation. Another important aerosol species, and indeed it is becoming more and more important as sulfate has been aggressively policed for air quality and acid rain reasons. So in places like Europe, it is being replaced by nitrate. Nitrate being the ion NO3-, typically found in the atmosphere either as nitric acid or ammonium nitrate. Its sources are mainly for the anthropogenic part, so from human activities, from agriculture and fertilizers. Then, very important species, mostly natural this time, that's mineral dust. So that's typically crustal materials which have been emitted into the atmosphere. So they're made typically of oxides, either silica or iron oxides, with some other chemical compositions that you can find in the earth crust, like calcium carbonate. Sea salt, of course, that's the aerosol you may feel in your hair when you've been at the beach for a long time. This is typically made of crystals of sodium chloride. And finally, a big species as well, those are carbonaceous aerosols. So either black carbon, which is basically pure carbon, or sometimes also called soot, and then a whole range of more complicated species, which are the organic carbon aerosols, which is carbon associated with hydrogen or oxygen atoms. So we mentioned that the origin of the aerosol is an important property. So in general, we distinguish between the primary aerosols, which are emitted into the atmosphere directly as particles, so directly into the aerosol phase. And then secondary aerosols, which are converted from gaseous precursors. So there's a conversion from the gas phase into the particle phase that happens in the atmosphere. So, question for you, can you think of examples of both primary and secondary aerosols? Mineral dust is sorry about the mic. Mineral dust is, yes, is a good example of a primary aerosol. Yeah, at the back. Sea salt is a primary aerosol as well. Yeah.
Black carbon.
Black carbon is a primary aerosol, absolutely. Any example of a secondary aerosol? Sulfate, yes, is a secondary aerosol. Yeah. Pollens. Sorry, say again? Pollens. There would be more of a primary aerosols then. Yeah, yeah. Oh, sorry, I didn't get you. Yeah, yeah. Okay, and nitrate is also a secondary aerosols, and most of the what we call secondary organic aerosols are also obviously secondary aerosols. Another way to distinguish between the origin is whether the aerosols are from human activities, so they are anthropogenic, or if they are of natural origin. And this distinction is particularly important in climate studies, where we want to know the impact of our activities on the composition of the atmosphere. Okay, moving on to another properties, which is the mixing state. So here the idea is that we've got this nice list of different aerosol compositions, but very often, and actually most of the time in the atmosphere, if you measure the chemical composition of a particle, you will find different chemical species in the same particle. So this is what we call an internal mixture, in contrast to the external mixture, where each particle has a distinct chemical composition. So in a way, if you represent that as a size distribution, you could say that in an external mixing case, you can have, for example, all of the smaller particles are black carbon, and then the larger particles are purely sulfate. But that would be very much of a simplification, because in the atmosphere, most of the time, the internal mixture is what we get. And the most frequent case, especially in polluted region, is a primary aerosols, for example, black carbon, which is coated by different material, by layers of sulfate or organics. And that's a good example of an internal mixture. Then, solubility. So the question here is the aerosol soluble in water or not? So the main example of a soluble aerosol is sulfate, which is typically present as small, very small droplets of sulfuric acid or ammonium sulfate. A good example of a non-soluble aerosol is either black carbon or mineral dust. However, as we just seen before, depending on the state of mixture, so the mixing state, insoluble aerosols can be coated with soluble materials and then become partially soluble themselves. And the importance of solubility is that if you can take on water, your particle size can grow. And this is what's referred to as the hygroscopic growth. And here I show again aircraft measurement of the hygroscopic growth of aerosols measured over Europe. So it is measured as a growth factor, which is simply the ratio of the moist aerosol to its dry radius. So obviously, so the growth factor depends on the relative humidity, so basically the availability of moisture. And at very low relative humidities, the aerosol typically is dry and generally remains at its dry radius until a given point, which is called the deliquescence point. And after that point, then the aerosol experiences a very rapid growth in its radius because it is taking on water. And you see that depending on the actual composition of the aerosol, so here there are different samples corresponding to different flights. But you see that, for example, here, this flight here in green, you see that the aerosol remains relatively close to its dry radius until about 70% relative humidity. And then there is a massive growth as a function of relativity, as a function of relative humidity, up to growth factors of more than 2. So the moist aerosol is more than twice as big as the dry aerosol. Finally, let's talk about a property that is perhaps less investigated, at least in the global aerosol model, is the aerosol shape. So, perhaps not surprisingly, dissolved aerosols are spherical, so they are basically very small droplets of water with a dissolved aerosol. Primary aerosols tend to have much more complex shapes, and here I show again the electron microscope picture of mineral dust particles, and you can see they are far from being spherical. In general, the shapes are complex. Some people have even tried and use fractals to describe the shape of those particles. So the shape matters because it affects the way the aerosols interact with radiation, and especially the way they can scatter radiation on their side. It can affect the importance and the strength of the chemical reactions that can happen at the surface of mineral of the aerosols. So, for example, mineral dust aerosols can be the site of chemical reactions that destroy ozone, and this is very much dependent on their shape and the presence of a small holes in the aerosol particle. Finally, it also affects their ability to serve as ice condensation nuclei, so their ability to be involved in the formation of ice clouds and ice crystals. For many reasons, especially for computing time reasons and because of the complexity of the different shapes, most of the time in most of the current climate and air quality models, when there is a need to specify the shape of the aerosol, then they will be assumed spherical. Okay. Okay, so that was basically the list of the aerosol properties, so how we characterize the particles, and what a model is supposed to be able to do when modeling the size distribution and the mass of aerosols. So let's now have a look at how it's done and how we can model aerosols numerically. Okay, so here is a very simplified summary of what we have to do in a numerical model to model aerosols. So we have to represent the emissions into the atmosphere. Then, while they are in the atmosphere, we have to represent their transport and their age. And finally, we have to represent the way they are removed from the atmosphere and the deposition fluxes. So that is the diagram for primary aerosols. And a question for you is, okay, let's say let's say we have black carbon, we emit 100 teragram of carbon per year. How much do we deposit? Say again, sorry. Okay, so let's consider a very long period of time and globally. How much do we deposit? Yes, exactly. We deposit the same amount as we emit. And that's because basically aerosols do not accumulate in the atmosphere. So on a global and typically annual average, emission and deposition fluxes are balanced. And that's an important concept in the modeling of aerosols. Of course, it is not only true of aerosols. Evaporation and precipitation of water is also balanced on a global scale in nature and in models. Okay, for secondary aerosols, things are slightly more complex because the emissions are not the emissions of aerosols, they are emissions of their precursors. So we start in the gas phase, and the model has to represent the oxidation and the conversion from the gas phase into the aerosol phase before getting the aerosol mass. Then we can do transport and aging and transformation of the aerosol and deposition. It's important to note that the gaseous precursor is also transported and is also deposited. So these are to be represented in the model as well. So there are three broad categories of models that are in use currently. So historically, started with the bulk mass models. So we're talking global models. So bulk mass models, they only simulate the mass. So they are not able to simulate the size distribution and then the number of the aerosol. So it means that since we still need some knowledge of the size distribution, we need to prescribe it globally. Prescription typically is done from some observation of the size distribution, either aircraft or remote sensing networks. In those models, by construction, the mass and number are co-varying. Since you compute the number as a function of the mass using the size distribution, if you increase the mass, then you automatically increase number, and vice versa. Then, at the other end of the spectrum of complexity, you've got sectional models. And here, what's done is that the size distribution of the particle, which is represented here, is decomposed into small size bins. The size of each bin depending, of course, of your computing resources and how long you've got to run your models. This is very powerful, of course, to represent the size distribution, although it's a bit more difficult and costly to represent the state of mixture in those models, because then you would need as many bins as there are mixing states in a way. Models have appeared about at the start of the century, and they are basically a compromise between the bulk mass and the sectional models. And the idea is to simulate both the mass and number of aerosols for the selection of species and the selection of mode. But instead of decomposing the size distribution, you just describe it as a superposition of log normals, just as we've seen a little bit earlier. And all you have to do then is simulate the value of the mean radius of your log normal. You can also try and simulate the width of the distribution, although most models tend to fix that. So this is very much a compromise between the two approaches. And it brings me to my next question is, what do you think are the advantages and disadvantages of each class of models? Which one is best? Yes, it's very, very cheap to run. Well, I mean, very cheap, considering computers now, yes. And historically, we started with bulk mass model because we were limited by computing time. Yes. So what is the disadvantage of a bulk mass model then? Yeah, absolutely. Because of this forced proportionality between mass and number, there are some processes that are very difficult to represent in those models. So basically, if a process increases mass without increasing number, then you can't represent it, or it's very difficult to represent in those models. What's the advantage and disadvantage of the sectional approach? Yep.
It can give the concentration at different cycles.
Yeah, it's extremely powerful to describe the size distribution. Yeah.
The disadvantage is it doesn't mix the different size beams. So it calculates the concentration in individual size beams. So it doesn't calculate it faster.
Well, you can, but it's true that it's more complicated than in other approaches. Yes. But of course, the main disadvantage is that it's extremely costly to run. It depends on basically the resolution you want to have on your size distribution. So the model approach is very much a compromise in terms of cost of the model and its ability to represent the right range of processes. Okay, so a little bit more mathematically that my simple diagrams with big arrows I showed earlier is the equation of conservation that by essence a model, a numerical model, solves when doing its job. So the idea is to write the time evolution of the concentration, so that could be also the number concentration. So it depends on the transport. So this here is the transport terms, which depends on the divergence of the wind field. Then you've got terms that describe the diffusion of the aerosols. So that's basically the idea that particles will tend to diffuse to occupy the whole volume. So here it depends on a coefficient of diffusion and on the gradient of the concentrations. Then, of course, you've got a source term, which gives you the aerosols that are added at each time step of your model, and a sink term, which measures the losses in aerosol mass or number at each time step. So your model, as far as aerosols are concerned, consists in a system of equations like that. So there's one equation for each species you want to include. If you want to include mass and number, then there's one equation for each. If you want to describe different species in terms of superposition of different modes, then you've got one equation for each. So the number of equations can grow rapidly. In the MAC project, we use an aerosol model, which is relatively simple compared to the state of the art now. So that's a bulk mass model. So that's at the simpler end of the sophistication, if you wish, and it includes the representation for the following species. First, sulfur dioxide, which is the gaseous precursor of sulfate aerosol. Then sulfate in just one mode, accumulation mode. Then two modes of black carbon. One mode which is hydrophobic, i.e. insoluble, and one mode which is hydrophilic, which basically it has become soluble. Same for organic carbon, two modes. Then three beans. So here it's a little bit like the sectional approach, but with a very, very coarse description of the size distribution, just three beans. So they cover typically the accumulation modes, and then two classes of coarse mode. And finally, mineral dust, again, three beans covering slightly different classes of sizes. The way the limits between the different beans has been chosen is typically to put, I think the idea was to put 70% of the mass in the coarse mode, and then the 30 remaining percent split between the two modes. And this choice is very much based on observation of the size distribution, aircraft observations or retrievals from remote sensing networks. So in total, you've got 12 tracers, so 12 conservation equations to solve, and it is very much a simple model. Even now in climate models, we use a more complex scheme, and we'll see one of those later. Right. So let's start the aerosol life cycle and how it is modeled. So we start with the emissions. So there are basically two different cases. First one is anthropogenic aerosols, so the aerosols emitted by human activities. Then we mostly rely on inventories for their emissions. So inventories are simply gridded data sets giving the emission rate, so kilogram of such species per square meter per second for the gaseous precursors and the primary aerosols you need to include in your model. Those data sets can be either global or regional, and they can be done at different time resolutions. The most used in general in global modeling is monthly resolution, seasonal, annual, or even decadal for very, very long climate trends, for example. In contrast, the emissions of natural aerosols are very often parameterized. So we try to compute them interactively in the model as a function of another variable that the model is able to resolve. So typically, that could be as a function of wind speed. It could be as a function of the soil moisture. It could be even a function of temperature. for biogenic processes, so for example, emissions from vegetation. So here in this table, I give you some indication of the strength of the different emissions for different species. So it's very much indicative. First of all, because you can have relatively large variability from one year to the next, and also because emissions are typically very uncertain. Claire Granier, Catilius, and Johannes Kaiser will talk a lot more about emissions during the week. But let's start with sulfur dioxide. So that's the gaseous precursor of sulfate aerosols. Typically, estimates of the anthropogenic emission rate between 50 and 90 teragram of sulfur per year, much larger than the natural emission rate. Ammonia, so that's emitted by agriculture activities and naturally by the ocean and by animals as well. Again, anthropogenic emission rate typically 2 to 5 times larger than the natural emission rate. Then we've got a class of gases called volatile organic compounds. So that's all the complex organic gases that we can emit in the atmosphere. And they will eventually form secondary organics aerosols. Here, the anthropogenic emission rate is much lower than the natural emission rate. But note that the natural emission rate, which is mainly from vegetation, is very much uncertain. So there's a little bit more than a factor 2 in the knowledge of that emission source. Moving to primary aerosols. Carbonaceous aerosols from fossil fuels, so that's combustion from transport and mainly from transport and power generation. There's no natural source. They're all due to us at basically a rate of between 20 and 50 teragrams of carbon per year. They are also emitted by biomass burning processes, so either by natural forest fires or by clearing fires for agriculture. They are also emitted by domestic cooking. 50 to 90 teragrams of carbon per year for anthropogenic, slightly less for the natural emission rate. So that would be fire started by lightning, for example. Mineral dust, huge emission rate, 1,000 to 3,000 teragram of dust per year, mostly natural. There is a small anthropogenic flux, and this flux comes from two main sources. First, cement industry, which tends to emit mineral dust. The other source is desertification. So the change in land use due to climate change, which is itself due to anthropogenic activities. So that does count as an anthropogenic aerosol. Finally, sea salt. Again, very large emission rate, 2,000 to 10,000 teragram of sea salt per year. Purely natural, although you could argue that the change in wind speed and the change in sea ice could also give an anthropogenic sea salt, but it's very uncertain, so it's not included there. And finally, DMS, dimethyl sulfide, which is a precursor of SO2, which is itself a precursor of sulfate. It's emitted by phytoplankton in the ocean, 10 to 60 teragram of sulfur per year for that source, which is mainly located over the oceans. There is a small source over land due to soil respiration. Okay, I guess I will stop after this slide. So, emission inventories. This is what we use to get the anthropogenic emissions. So they tend to be estimated for different sectors, typically transport, shipping, aviation, power generation and industrial, residential and commercial, agriculture, and biomass burning. So each time we burn wood, it also includes a natural component from fires started by lightning, but it's very difficult to separate in those inventories the source. I will not go into too much details, but you can see Claire's lecture later in the week. Johannes is scheduled to give a talk on the biomass burning emissions, and Cathy will have a working group on emissions. So they will give much more details on how those inventories are done. Just to see what they look like, this is the year 2010 in one of those inventories. So that's a CIMIP 5. So that's an inventory which has been made to drive long climate simulation. So that's the emission of sulfur dioxide. First, looking at where they come from, you see that most of it is due to power generation, so power plants, mainly the burning of coal, especially low quality coal is a good source of SO2. And then industrial, shipping, and transport are also large sources of SO2. Looking at how they are distributed across the globe. So first, watch out for the logarithmic scale here. So we start with a very small rate, up to 50 kilogram of sulfur per square meter per second. So not surprisingly, the SO2 emissions, those are the anthropogenic emissions only, they are centered over the industrial centers of the planet. So Eastern US, Europe, with especially Eastern Europe, the Middle East, India, and China. You can also see over the ocean those tracks of emissions, which are mainly due to shipping. So those are the main shipping lanes connecting the different economies across the world. Another example, carbonaceous aerosol emissions. Here the picture is quite different. The main anthropogenic contribution is from biomass burning, so clearing fires for agriculture. And there is also about a fifth of the emission due to domestic sector, so that's cooking stoves used in many countries for cooking. Here, again, non-linear scale, you see that carbonaceous aerosol emissions are mainly located over in the South Hemisphere, so South America and